All right, why don't we go ahead and get started. So welcome back everybody to EE290C. Hope you had a good break. So obviously project phase 2 is out. I did receive everybody's phase 1 reports. I've sort of started going through them and I'm just collecting all the feedback and I'll sort of send that out en masse. That'll probably happen later on tonight. Other than that, before we sort of dive back into material and stuff like that, any questions on the project or issues or anything that people are coming up with?
How much level of detail do you expect for this phase of the project?
How much? So for this phase of the project, it's really up to you. Obviously, the more detail you've got, the better it'll be for you later on down the road, because there'll be plenty of other things that you'll be filling in detail. So if you've already got, like a whole size design, you know exactly what it's going to look like, great. If not, that's not to say that you have to have that by this point. But again, the more sort of detail you've got, the better it'll be for you. Maybe just kind of give you a little bit of a roadmap. Phase 3, basically the intent will be that by that point you'll have at least a very good idea, if not sort of reasonably complete implementations of kind of the whole timing parts of things. And then phase 4 will really be sort of putting it all together and really checking that the whole thing works and that you're actually getting the specs that you'd like and so on and so forth. So that's why I said, while you don't necessarily have to have things complete by phase 2, if you don't have them done, then you'll just be sort of playing catch up sort of as we go along. So again, the more you can get done, the better, but that's not to say that you have to be completely done. So that's just kind of to give you an idea of roadmap where we're going from here. More questions on the project? Yeah.
So I know people are going to hate me for asking this, but are we expected to take in the wire caps as well into account? Or?
Okay. So the question was, are we expected to take in the wire caps into account? So I'll put it this way. If you know that there's going to be a wire there and you can estimate pretty reasonably well how long it would be, then I would say it's a good idea for you to include it. I don't have necessarily a script or something that's going to be like, going and automatically checking it or anything like that. But remember, the intent is for you to sort of do something as realistic as possible. And if you know that you're going to have, as an example, a 1 millimeter or 500 micron or even 100 micron wire where you're only dealing with minimum sized transistors, then good idea to roughly include what that wire cap would actually look like. Now, again, I'm not going to be running post-layout extraction because you're not going to be doing layout or anything like that. But, again, if it's pretty obvious that there's going to have to be some wire there, you really should go and include that. This is assuming, all you guys that are here, I'm assuming you've taken 141, you've taken 241, you've taken 240, taken 142, all those other things. So, I'm assuming you guys are good designers by this point so that you'd actually make some effort to make things reasonably realistic. Having said that, I didn't give you any process corners or anything like that, so I have allowed you to cheat somewhat, but don't cheat too heavily because we want to make this as reasonable as possible. And of course, I will read things at the end of the day, and if I see something that's kind of obvious in terms of, okay, hey, come on, you really ignored something here that you should have included, I'll take that into account when I do the grading. Other questions on project or material or anything like that? How many of you guys, how many of you guys have at least looked at phase 2? Okay, good. So remember, next week is actually, you guys are going to be up here giving presentations. I haven't decided yet. We probably won't necessarily webcast those, but you've got about a 15-20 minute time slot, so make sure you're prepared to actually say something. We'll probably schedule that so that it's about 10 to 15 minutes, intended to be sort of the quote-unquote presentation, with 5 to 10 minutes sort of time in order for people to actually ask questions and give feedback and things like that. So it's still going to be intended to be fairly interactive, but keep track that you will be doing that. Yeah.
So do we need to finish the presentation by Monday too, or can we sort of?
Yeah. So I think that's how I wrote it up in the project report. Only just so that only just to keep things fair in terms of the people who end up presenting on Thursday, so they don't get an extra 2 days to do stuff that people who are presenting on Tuesday, haven't had a chance to do. So I guess what I could do is I could let everybody email me the slides by, let's say, start of lecture on Tuesday, and then I guess that would be fair, and then I'll just, make you use the slides that you actually sent me or something like that. Does that sound reasonable to people, or? Okay, and if you want to bring it on USB stick or something, that's also fine. Okay, other questions, or? Maybe just to get a quick poll. So how many people are planning to do just 10 gigabits per second? Let's say, well, let's just do it by data rate. How many are just shooting for 10 gigabit per second? Okay, let's say between 10 and 15. That's, I guess, 1.5 groups or something. And 15 to 20?
We are doing 16.
6?
16.
Oh, 16, okay. Anyone over 20? Oh, come on, there's nobody like super aggressive and wants to do, no, I'm just kidding. Okay, just curious. All right, so unless there's any other questions on the project, let's go ahead and actually dive back into the class material. So we've been spending the last couple of lectures talking about phase lock loops. And in particular, this last lecture, we sort of dived into a bunch of the sort of component details. But where we ended up last time was talking about the fact that, particularly if I'm going to be using a ring oscillator-based PLL, where I'm really going to be covering a pretty broad frequency range. Well, because it's a ring oscillator, pretty much anything that changes in the process, and by ring oscillator I mean almost literally just a pile of inverters tied back to back, pretty much anything that's going to be changing in the process will also change the characteristics of that oscillator. Well, if you think about it, if the oscillator characteristics change, then the PLL characteristics will also be changing. Now, as we sort of drew out in gory detail last time, that's pretty bad news because it says that, especially if you want a, let's say, reasonably aggressive loop bandwidth, something close to kind of the highest you could possibly get, if you have a large amount of variations that you can't compensate for, that would force you to basically back off on the nominal loop bandwidth that you'd get, and then in fact, in the worst case, you'd get even much lower loop bandwidth than that, which, as we'll talk more about today, has some pretty bad implications from the standpoint of the jitter you could possibly get. Okay? So to basically try and counter that, there's this idea that, as I think I mentioned last time, was, I believe, originally published by a guy named John Mattiatis back in the early 90s. I believe it was EE290C where he sort of first talked about this, which was the idea of self-biasing. Okay? So the idea of self-biasing is essentially that we want to make the loop characteristics basically set only by two things. And so the first is just set by essentially what's the reference frequency. Okay? And the second is just ratios of components. Okay, or component values to be precise. Oops. Okay, so the idea here is that if I can really do that, then if I can make everything to basically slave to just what's the reference frequency and ratios of component values, then at least in principle I should be able to make everything well controlled enough that I really can exactly hit that loop bandwidth that I'd like, or just exactly hit whatever the loop characteristics I'd like to be. Okay? So the key question, of course, is how do you actually do this? Now, it turns out that building a loop to be self-biased is not quite as complicated as you may at first think, but understanding why it really is self-biased involves a little bit of math and a little bit of sort of manipulating things and looking at how things got there. So that's kind of what I want to do in the next 2-3 slides or so, just to make sure that you guys understand where is it that this general technique, how could you actually come up with something that would do this, okay? So to do that, we sort of just have to first remind ourselves what the sort of transfer function of the PLL looks like from the standpoint of the reference phase or reference clock coming in to the reference phase at the output, okay? So again, just as sort of a reminder, if I have some reference phase, I go through some PFD, and then let's pretend or let's assume that we're building a charge pump PLL, which is kind of the nominal structure we've been talking about. Of course, I'll then feed that into some loop filter, pass that, of course, into the VCO, and then, as an example, well, I'll just make life simple. Let's ignore the fact that there's really a feedback divider. It's pretty easy to include that, but let's ignore it for now. And then I just have that output feeding back into my PFD. Okay? Okay, so if we were to sort of write out the loop transfer function for this, in other words, if I wanted to know what was phi out over phi ref, of course, all in the S domain, then basically it's a fairly standard feedback loop. Let's just assume that the PFD gain has been normalized in some way. And by the way, I'm going to write out sort of the shorthand form of this, where I'm going to be dropping factors of 2 pi in various terms here and there. I'll come back a little bit later and sort of show you a more formal way of doing things, but I'll give you the shorthand version, which turns out to be still, let's say, correct. But seeing exactly where it came from, you just have to sometimes walk through the whole loop. Okay? So basically, if I want this transfer function, then again, I can sort of use my standard feedback kind of thing, where I have some feed forward gain A of S. And in this particular case, I'm tying it into unity gain feedback. Right? So this is my phi in, that's my phi out. Right? So if I'm doing that, then as usual, my transfer function will just be A of S over 1 plus A of S. Right? That make sense to everybody? Or? Okay, good. So the only trick here is just what is that A of S? Okay? So basically, if I sort of walk through this loop, the PFD is in some senses just converting timing error into something sort of unitless, or really maybe normalized to sort of how big is that timing error compared to the whole reference period. Okay? And if you sort of think of this in the context of the charge pump, you could sort of say, well, if my error was like an entire reference period, right, then I would sort of be dumping either up current or down current during that entire time, right? So you can kind of interpret these two things together as just telling you, for a given phase error, how much sort of current flows into the output from that charge pump. So sort of the gain of that just ends up being essentially whatever the current of that charge pump is. Okay? So then, of course, once I go through the charge pump, I just pass that through, or rather to get to a voltage, which is really what's controlling the VCO there. I just take that current and I multiply it by the loop filter impedance. Right? So for this particular loop filter that I've drawn here, what is that impedance? And let's just say this is R and this is C. So what is the impedance of that loop filter? What's the impedance of a series RC network like that?
Plus 1 over SC.
Yeah, it's just R plus 1 over SC, which I'm just going to rewrite slightly as being 1 plus SRC over SC. Okay, and I'm just writing it that way to make it clear that there really is an integration. Okay? So I take that current, I multiply it by the impedance of that loop filter, and then I have a control voltage that goes into the VCO. So what did we say was the relationship between control voltage into the VCO and phase at the output?
KVCO.
Yeah, it's just KVCO over S. Okay? So that really is my A. So now my whole transfer function is just that plus, obviously, or over 1 plus A. So that's, of course, the same thing, just repeated. Okay? So again, nothing magic here. Usually when you write this out, you sort of rearrange the terms a little bit to sort of get into, let's say, a standard second-order system form. And you'll see why I do that in 1 second, because if we get into that form, it'll be easier for us to sort of keep track of which parameters are varying how, and basically what does that imply about how the components need to be tweaked in order to make sure that they will be self-biased correctly. Okay, so the standard way you'll actually write this is something like the following. You'd actually instead say that it's something like essentially KVCO ICP, which is just charge pump current, times 1 plus SRC, divided by S squared C plus KVCO ICP times 1 plus SRC. Okay? And actually, I'm just going to simplify this even just one step further. So from here, obviously, all I did was just take the things on the denominator and push them up. So if I simplify that just one step further, what you'll basically end up with is something like 1 plus SRC divided by S squared C over KVCO ICP plus SRC plus 1. Okay? So now by writing things this way, I've kind of gotten it into sort of your standard second order system form. Right? So you have 1 plus S over some 0 frequency divided by S squared divided by some essentially natural frequency squared, which is usually referred to as omega n, plus S times essentially some damping factor divided by the natural frequency plus 1. Okay? I'm assuming this looks very familiar to everybody. If not, let me know or something like that. Okay, so again, the reason I wrote things in this way is because what we can now do is look at what is it going to take for us to make sure that everything is sort of sitting in the right spot. Okay? So if you sort of think about it, there's really only 2 or maybe 3 parameters that you really care about here. Okay? So if I've got the second order system, what's really only the 2 or 3 parameters I've actually got available to me? What are the sort of degrees of freedom I can play around with? Yeah?
The
quality factor and the bandwidth?
Yeah, so basically the only things I can really play around with here are the natural frequency or the bandwidth, or rather the omega n as it's usually referred to, and the quality factor, which from whatever reason PLL people are more like control theory people, so they like to refer to the damping factor rather than the quality factor, or zeta. But basically those are the only two degrees of freedom we really have here. In a generic second order system, you would have been able to tweak the zero frequency as well. But notice the zero frequency is directly set by that damping factor because of the way this loop is built up. Okay? So the name of the game is really going to be, how do we tweak the component values to make sure that the damping factor and the natural frequency track with whatever we want them to be. Okay? So now, okay. So first question, let's just first look at the natural frequency. But before we get into that, let's just remind ourselves, what is it that we want the natural frequency, which you can kind of interpret this as being the bandwidth of the loop. What do you want that to do? How do you want it to, what do you want it to be set by? Let's assume you want it to be as high as you can make it. What would you want to set it to?
Omega f by 10.
Yeah, exactly. So if you could, if you could do whatever you wanted to, what you'd basically want is that omega n to be roughly the reference frequency divided by 10, right? So in other words, like we said before, we want the characteristics of this loop to be set by the reference frequency and by just some ratio that we're going to set by basically designing certain sizes of components. Okay? So if you take a close look at sort of what I wrote over here, what you can basically pretty quickly figure out is that the natural frequency, of course, is just set by this term right here. So if we just write that out, then that tells you that the omega n is equal to square root of kVCO times the charge pump current divided by the loop filter capacitance. Okay? Okay, so now to see how we're actually going to get something to be self-biased, what I'm going to do is just sort of make a couple of assumptions and then come back and try and prove that indeed if I do things that way, then I can actually make the loop self-biased. Okay? So the first hint that I'm going to give you is, in order to make things self-biased, the first sort of trick I'm going to play is actually make the charge pump current proportional to the VCO current, okay, through some scale factor. Now, the reason why this actually turns out to be good, again, we have to go through a little bit of math to see why that works. But before we do that, just right off the bat, if I make the charge pump current proportional to the VCO current, and remember that the VCO is just a CMOS ring oscillator. In terms of sort of, let's say, physically some of the parameters inside of that oscillator, like capacitance, voltage, etc., what sets the current in that CMOS ring oscillator? What is that proportional to?
Number of stages in the ring.
Okay, so there's some number of stages. That's true. What else?
Size of each stage.
Okay, size, like, what do you mean by size? You're right, but what do you mean by that?
Width. The capacitance.
Ah, there we go. Okay, so there's a capacitance, right? What else?
Frequency.
Yeah, okay, so the VDD. Now, remember, the way I'm sort of typically going to build this is I'm going to take this control voltage and use that to set the supply of some ring oscillator, right? So instead of writing this as VDD, I'm actually going to say that the VDD of the oscillator is my PLL control voltage, okay? What else do I need to get the current?
Frequency?
Yeah, the frequency of the oscillator, okay? All right, so now just notice one thing here, which is, oh, yeah.
I have a question. So what do you mean by IVCO? Is it the average current? I mean, what?
Yeah, so, no, I guess I don't have the picture drawn here, but I'll draw it. So remember we said that the way we were going to be building this loop up was basically we were going to take the control voltage from the loop filter and use that to essentially, basically through a regulator, set the supply voltage of the VCO, right? So in other words, there's some average current flowing through here, right? That's the average current that I'm going to be copying and using to set my charge pump current. Okay, and I'll draw a picture a little bit later on in detail of sort of how you do that, but basically that should already give you the idea. Okay? Okay, so now, remember we said that we wanted our natural frequency to be proportional to the reference frequency. And I just said that sort of, I was just going to tell you that we were going to make the charge pump current proportional to the VCO current. just sort of off the top of your head, why does it look like it might be useful to make the charge pump current proportional to the VCO current? Just let's say dimensionally, or let's say from the standpoint of things scaling with each other, what's nice about making the charge pump current scale with the VCO current? I'll give you a hint. What is it you wanted the natural frequency to be proportional to?
Omega ref.
Yeah, it's supposed to be proportional to omega ref. Do you see anything in the charge pump current expression that's proportional to omega ref?
Oscillation frequency.
Yeah, the oscillation frequency, right? Because remember, if I told you the divide ratio, then I also know what is, the VCO frequency when I'm locked should just be some multiple of the reference frequency, right? So in other words, what we're basically saying here is that this now charge pump current is proportional to essentially the capacitance times the control voltage times the reference frequency. And again, I'm dropping factors of 2 pi and divide ratio and things like that, but don't worry, those are all just fixed factors that you can figure out what they are and make things work. Okay?
But then won't it be proportional to square root?
Ah, okay, great. So as you just said, now if I follow that, then what I've basically gotten is, because I only have this ICP on the top here, then unfortunately I've only gotten my omega n to be square root proportional, right? So in other words, if I want my thing to be self-biased, what this is basically saying is that I still have a condition on KVCO, right? So if I want to be self-biased, what does KVCO need to be proportional to?
Frequency.
Yeah, it has to be proportional to the frequency. So it has to be proportional to something like either FVCO or the omega ref. And what else? What else do I need it to be proportional to?
C filter.
Well, you're sort of right, although remember, if I have a capacitance over a capacitance, I can use that to just tweak what the ratio ends up being, right?
Just some other capacitance that's...
Yeah, but and maybe I'll just plug it in over here. So notice, if I just take that and I plug it into there, I'm going to get something like omega n is proportional to KVCO times C stage over C filter times omega ref times VC, right?
Right.
Okay, so what do I need to knock off?
Should be inversely proportional to the control voltage.
Yeah, there we go. I want it to be inversely proportional to the control voltage, right? So notice if I can do this, then I can get the whole thing to be self-biased, right? Because what will happen is the control voltage will fall out, the frequency will just multiply with the frequency, and everything will magically work out, okay? So now the key question is KVCO really proportional to FVCO divided by VC? Okay, that's the million-dollar question now. Okay, so, well, what is KVCO actually set by? In other words, is this really going to be the case?
That is it. That's the definition, right?
Not necessarily. So you're right only in the sense of if I do like a large signal, right? Like if I put a big delta and a big delta down there, you're right that would be true. But that's not necessarily actually true for any, if I took the real derivative at a given bias point, then that's not necessarily true, right? So maybe just, as Shiva was saying, to find KVCO, what we need to do is basically take the derivative of the oscillation frequency with respect to the control voltage, right? Okay, so to do that, then we kind of need to know what is the frequency of the oscillator to begin with, relative to the control voltage, right? Well, okay, so what is the frequency of the oscillator, or at least what is it proportional to? And again, just think digital now. Because remember, my oscillator is just a pile of inverters.
1/2 times number of stages times the propagation of one stage.
Okay, that's right. So you said it's basically proportional to 1 over the number of stages, and actually twice that, times the delay per stage. Okay? So all of the things that are kind of fixed by design, like the number of stages and that factor of 2, I'm just going to drop for now. Because again, I just want to show the proportionality to make sure that it's clear how things are self-biased. Okay? So what is, in terms of the delay of each stage, what is that set by in terms of, and remember, what we're trying to do is show at the end of the day that this is going to hold. So what is the delay of each stage set by? control voltage.
Per of each stage.
Okay, so let's just, you know, all the parameters you guys mentioned are absolutely correct, but let's just come up with an expression. So what is that frequency proportional to? Let's say based on the current, based on the VC, based on the capacitance. What is that frequency proportional to?
Voltage. The voltage.
Is it proportional to the voltage? There we go. Okay, so you said CV over I. CV over I is the delay of a stage, right? So if I'm asking about the frequency, I want 1 over the delay, right? So in other words, that frequency is proportional to ion divided by the C of the stage times the VC, okay? And again, this is just 1 over delay, basically. And again, I'm dropping factors of 2 and things like that because, again, all we're looking for is proportionality here, okay? Okay, so now we just said that I want the derivative, right? So before I sort of do that, I'm just going to make my life a little bit easier, and this is where I'm going to have to be waving my hands the most furiously because this is where the math, it's not really that bad, but just you have to do some more math if you really want to prove this, or really want to get this to absolutely correctly work, which turns out it doesn't quite, but it's close enough. So if I was back in the good old days where I could ignore threshold voltages and I could ignore short channel effects and all these other sort of minor annoying details, what would I say that that ion is proportional to?
Squared.
Yeah, I would say that ion is proportional to VC squared, right? Okay, so now notice this is going to be something kind of magic. If ion is proportional to VC squared, then I can basically say that KVCO is proportional to essentially VC divided by the capacitance of each stage. Okay? There's again some scale factors that I'm just dropping here, but I just plugged in that ion proportional to VC squared. Okay? Well, what's nice about that is that basically, if I take the derivative of this, or rather I should say that, did I do that? Oh no, excuse me. Sorry. This was actually the frequency of the VCO, right? So now if I take the derivative of that, then that says that it's just proportional to 1 over C stage, right? Because if the frequency is proportional to VC over C stage, then the derivative is just proportional to 1 over C stage, okay? Well, remember we said that we wanted KVCO to be proportional to FVCO over VC, right? But what is FVCO?
Over CST.
Yeah, so FVCO, we just said, was the control voltage divided by the capacitance of the stage, right? In other words, that says that what we're really looking for is for the KVCO to be proportional to VC over C stage times 1 over VC, which of course is just 1 over C stage, okay? So in other words, nicely enough, if indeed my on current was proportional to the square of the control voltage, then indeed I've gotten my criteria to match. Okay? In other words, I've made it so that KVCO is indeed proportional to the VCO frequency divided by the control voltage. Okay? Does this kind of make sense to people, or? Okay, so what's, let's say, some of the most hokey things about this? What's going to sort of cause this to break? What's going to make it so that I don't exactly get the self-biasing that I really wanted? Where's the place I had to sort of wave my hands the most furiously to get this to happen?
Saturation.
Yeah, so what I had, the sort of the place I had to wave my hands most furiously was right here, right? I basically had to say that, oh, I have this nice magical transistor that, is still quadratic and has no threshold voltage and all these other, let's say not so realistic things. So it turns out that despite the fact that this isn't really exactly true, it still tends to match closely enough, right? So you can actually go through the full equations where you make this proportional to some alpha power law or do some velocity sat. Turns out it still actually works reasonably well, or I should say well enough that you can get things to sort of track within about plus minus 10% or so, okay? The only thing that ends up being really bad is if I throw in if I make myself really close to the threshold voltage. Okay, because once you start getting close to the threshold voltage, basically all of these things about, really these expressions here, where I've had to approximate what the KVCO really was, basically fall apart. Okay? So kind of the bottom line is that this does indeed work pretty well, even though the assumptions are a little bit hokey to get there, as long as you make sure that your oscillator is really working very well in the sort of super threshold regime. Once you start getting close to subthreshold, bets are off in terms of really making the things track with each other. Okay? There's probably some other, let's say, tricks you could come up with to make it work in subthreshold, but basically making it work in both regions is really, really tough. Okay? Does this make sense to people, or? Okay, so this is indeed sort of how you make things work for the natural frequency. So really the only parameter we've got left is the damping factor. Okay? So let's see what sort of is going to happen with that. So just as a reminder, the transfer function that we're working with in terms of our, let's say, standard PLL is just something like, and I'll be a little bit more careful. Okay, that's kind of our standard transfer function that we're working with. And remember, the standard second order form looks something like 1 plus s over a 0, s squared over omega n squared, plus 2 zeta over omega n, s, plus 1. Okay? So again, the only reason I'm sort of writing this out in this level of gory detail is just we have to figure out what is that damping factor, or what is the zeta, as a function of kind of our loop parameters. Okay? So if you basically track these two things, what we're basically saying is that 2 zeta over omega n should be equal to r times c filter. Okay? Right, so I just basically set those two terms to be equal to each other. Okay, so if you recall what, the omega n was in the first place, well, okay, I can just solve this first. This will just be 1/2 r c filter times omega n. Okay? Which, if you remember, that omega n, what we're going to want to do is make it proportional to the reference frequency in the first place, and the reference frequency is going to end up setting the VCO frequency. Okay, so what I'm kind of getting at here is that we basically want to make this whole thing be proportional to 1/2 r c filt times the VCO frequency. Okay? Because again, the VCO frequency is just related through some integer factor to the reference, or to the natural frequency, which is again related to the reference frequency. Okay? Does this make sense to everybody? Okay, so the reason I wrote this out this way is hopefully this should make it clear what you actually want to make constant in order to get things to work the right way. So, by the way, what's sort of going to be our goal for the damping factor? What do we want it to be? And I don't need a number, just, conceptually, what do we want it to be? What's that damping factor important for?
Stability.
Yeah, stability, right? So there's going to be some number, typically something like either 1 or 0.7, somewhere in that ballpark, that you're going to make sure that you get that number for the damping factor, right? So notice it's good news here that, this expression that I've written here is dimensionless, right? Because it's a time constant times a frequency. So that gives you a dimensionless quantity, which is indeed what the damping factor is. So if we want that damping factor to be constant, that's basically telling us that we want the RC product essentially to be proportional to 1 over the VCO frequency, right? So if we make that RC product proportional to 1 over the VCO frequency, then indeed this damping factor will also be constant, right? Okay, so what do you think you're going to end up wanting to tune? Are you going to tune the resistance or the capacitance of the loop? Or both? What do you guys think? Who votes for tuning the capacitance? 1, 2, 3, 4. Who votes for tuning the resistance? 1, 2, 3. Who votes for tuning both? And there's going to have to be a bunch of hands, I guess, associated with this, just, subtracting out who previously voted. Okay, so whoever voted for capacitance, why do you want to tune capacitance?
It's easier. It's linear, right?
Linear with what?
You can have a parallel combination, and also because you have RC series, your bottom plate won't affect. Whereas the
Okay, but so let's actually sort of draw how we're going to do that. Just over in this, let's just use this picture over here. So you're saying you want to tune the capacitance. So how are you going to do that?
just put an array,
Put an array of what?
array of capacitors.
Oh, but remember, so you're saying like a digitally switched array or something like that? Yeah. Oh, but so you could do that, but notice that with what I did over here, I needed exactly 0 digital control logic, right? Simply by me taking that bias current and feeding it back to the charge pump, I automatically got the natural reference frequency to track. So I want the same solution. I want something that with me doing absolutely nothing, other than building it the right way, I get my things to track with each other. Okay? So you're right, you could indeed do that, but that's... Say that again?
Use a MOS cap.
Okay, so if you use the MOS cap, how are you going to tie it up to make it track the right way? And notice you have to make this RC product track 1 over the VCO frequency. So how are you going to do that? By the way, there may indeed be a way to do it, but I'm just curious what it is. Yeah.
Use a switch cap.
Use a switch cap. How are you going to use a switch cap? Say that again.
Use a switch cap to synthesize the resistor, so you lock the as time constants.
Okay. So you're right. You could indeed do something like use a switch capacitor to actually control the R. But so now what you're actually saying is that we control the R and not control the C.
Yeah.
Right. Which, by the way, I agree with. It's actually much easier to control the R than it is to control the C in this particular context. Okay. So you're absolutely right. You could indeed use a switch cap resistor, and you'll actually get exactly the right behavior. Turns out that has some other benefits associated with it, because if you do it right, it actually helps smooth out the reference spur. But actually, it turns out there's even another, even simpler way of doing it, which will still get you the same effect. Okay? So it turns out if we want to build a variable resistor that does the right thing, turns out actually all we need is a triode CMOS transistor.
Using the control voltage? Or?
Yeah, and you'll see in 1 second exactly how we do this. Okay? Because basically if we have a triode CMOS transistor, and again if we assume that the ion is proportional to VC squared in SAT, right? Then in linear, that basically implies that our resistance is proportional to 1 over VC, right? Because again, if you sort of think about it in triode, the triode ID SAT would just, or the triode, the IDS would just be some K factor times VGS minus VT times VDS, right? So the resistance is just something like 1 over VGS minus VT. If VT is small, then VGS is just the control voltage. Okay? Okay, so if our resistance is proportional to 1 over that control voltage, then basically what we're saying is that our R should be proportional to 1 over FVCO times the filter capacitance. But hey, remember, FVCO over here was just proportional to VC over the capacitance of the stage, right? Right, so all I did was I took the FVCO and plugged in that it's proportional to VC over the capacitance of the stage. Well, so that basically tells us that that thing is just proportional to the capacitance of the stage over C filter times 1 over VC. Okay? So in other words, again, if I have a triode MOS transistor, it's exactly going to give us the 1 over VC dependence that we need to make this whole thing self-biased. Okay? Does that make sense to people? Or? So again, this is actually kind of cool, because as you'll see in 1 second, I'm going to be able to draw a PLL that essentially by me just doing basically 2 things, quote-unquote, the right way, I will automatically get it to track across process, temperature, voltage, all of the other stuff that you usually have to worry quite a bit about. Yeah?
So the 2 C's are different, right? This one is like MOS cap, the other one you build from MOM caps.
Not necessarily. So that's a good question. So you're asking, like, basically if I look at this loop filter here, if this cap is a MOM cap and the cap that's inside of my oscillator is built from something else, don't they actually not exactly track each other? And you're absolutely right. If you don't build those kind of the same way, then indeed you'll have some mismatch in the tracking there. The good news is that because you have to sort of avoid the subthreshold region because of the IV characteristic problem anyways, usually both the MOS cap and the MOM cap are relatively constant versus the control voltage. So if you kind of get the matching nominally right at a reasonable supply voltage, then it still usually tracks pretty well. That's not to say that this is precise to within 10 bits of precision, but if it's good to within plus minus 10% or so, then basically you've gotten the vast majority of the benefit that you really wanted in the first place. But you're absolutely right. It's not that this is perfect. It's actually not perfect for a bunch of other reasons as well. But indeed, the mismatch between the caps is one of the potential issues in terms of not making this work exactly correctly. Yeah?
So won't you have to switch the R and the C in the stack to
Ah.
get this to work?
Okay, that's a great question. So let's actually draw how you really build this. Okay? Because your question is actually a great one, because if you build this the wrong way, it ends up being pretty nasty. Okay? So let's see how you'd sort of build this. And some things I'll draw conceptual, and some I will draw the real detail. Okay, so we're going to have our phase frequency detector with some feedback there, of course. That is going to feed the charge pump. Okay? Now, again, remember with the charge pump, what I was going to try and do was actually have it work off of the bias current, or rather the current flowing from the VCO. Okay? So the way I'm going to do that, and I'm just drawing a couple of transistors here. This is slightly more conceptual than real, but it's just to sort of make the point, so to speak. And I'm just going to assume that I've got some loop filter there. I'll come back and draw it in 1 second. Then I've got my regulator over here. Okay, that's of course just feeding my ring oscillator. And then, of course, that ring oscillator will have some level shifter, go into some divider, and feedback. Okay? So what would be a really convenient way for me to basically grab the current that's flowing through this oscillator in any case? Is there some, one wire you can add here that will magically give me that current? Or maybe one wire and one transistor to be precise.
Just mirror it.
Yeah, I just need to mirror it, right? Well, hey, this transistor here that's inside of that regulator, if I've done things right, then it's going to be in saturation, right? So basically, if I want to mirror that current, really all I have to do is take that gate control voltage and feed it to another PMOS transistor that's kind of biased at the same, that's just ratioed in terms of its size, right? So that it ends up being biased at the same current density. Okay? Does that kind of make sense? So in other words, this PMOS transistor here, which again, this is kind of more conceptual rather than you don't really exactly build the charge pump this way. All it's doing is just grabbing the regulator control voltage into that PMOS power device to create a copy of that current. Okay? So of course, you're going to have another copy of the current with another mirror over here just to get the pull down side as well, but that's not too big of a deal, right? Once you've mirrored it once, mirroring it again is easy. Okay? So now actually the only trick is, how do you build that loop filter? Okay? Okay, so there's kind of two options here. Okay? So I'm going to draw, I guess, the first one that Richie was asking about. And then maybe we'll see if that one works or if we have to do something else. Okay? So the first one that Richie was thinking about was saying, well, okay, if I want my resistance to be controlled by the control voltage, then it would be kind of nice to do something like this, right? Because now I have an NMOS transistor down here. The gate is set by the control voltage. Source is just ground, so that VC sets the resistance there, right? Okay, so you could indeed do this. Turns out it's not necessarily the best way of doing it. So there's one very subtle issue that tends to cause a problem with this particular design. So how am I building this cap right here? Just generally, what are the kind of the two options I've got?
MOS cap or metal?
Yeah, it's got to be either a MOS cap or a metal, right? Any capacitor that I build, what does it always have coming along with it, whether I like it or not?
Bottom plate.
Bottom plate, right? Okay, so if I just add, and by the way, bottom plate, of course, means both bottom and top plate. So I'm going to have some bottom plate there, quote unquote. And I'm also going to have some bottom plate right here, okay? Now, why is this potentially problematic.
You add more poles to your face lock.
Yeah, exactly. I'm adding extra poles into the loop filter, right? Because basically, this cap down over here is just directly in parallel with that resistance down there. And remember, that resistance was supposed to be your stabilizing zero, right? You wanted that to be basically at high frequency, really just a resistance, okay? So you can still potentially get this to work, but if you have a really large bottom plate, then it'll basically limit the loop bandwidth that you can actually achieve, okay? So it turns out this is not necessarily the best way to do it, but the good news is there's another way to do it, which works very, very nicely. And so I'll give you a hint, and I won't, draw the full thing, but I'll give you a hint. You'd like to put it back into the same order I had it before. So how can you do that and still get a voltage-controlled resistance? With, of course, that voltage control being from the control voltage itself.
Can you use a PMOS and invert the voltage? Or?
It turns out I don't even have to invert it. I just have to use a PMOS. So how do I hook up the PMOS? So I've got a PMOS device. I've got VC right here. What do I have to put at the gate? By the way, this is not a trick question. It's actually the simplest thing you could think of to put at the gate.
Ground.
Yeah, you just put ground, right? Because just like before, my control, my gate, my VGS is just VC, right? So indeed, if you do things this way, good. Because notice, bottom plate, over there, irrelevant because it's just ground to ground. Bottom plate over here, also basically irrelevant because it just gives you more cap, right? And now if you really wanted the third order cap, you can intentionally place as much as you'd like on that third order point. Okay? Does this make sense to people, or? Okay, so, and just because it's a little bit cluttered, I'll maybe do this in a different color. This thing right here that I'm circling right now, that's really the way you want to do it. Okay? You really do want to use that PMOS version, simply because of that bottom plate issue that we just talked about. Okay? But now notice, simply by basically playing these two tricks, and of course making sure that I do a reasonable job with making the wire capacitance in the VCO, or really the wire to gate ratio, track reasonably well with kind of what I've done inside of my capacitor and things like that. If you just basically build things like this, turns out it will indeed actually track quite well across process, voltage, temperature, even down into sort of very, very aggressive technology nodes. So this is indeed the sort of very common style that you'll see for most of the clock generation PLLs out there these days. I should mention that, as I said earlier, John Maniatis was one of the first people that sort of came up with a self-biasing idea. He actually did it with a slightly different VCO structure. But this particular version that's really using inverters for the oscillator itself was done by also Stefanos Sideropoulos. And this is, I believe, from VLSI 2000. Okay, so he was the one who basically worked out how you do this self-biasing in this supply-regulated ring oscillator context. Okay, and indeed, it's really just as simple as mirroring the VCO current into the charge pump, and then essentially coming up with a resistor that just essentially tracks the IV characteristics of the devices in the oscillator in any case. Does this make sense to everybody, or? Yeah.
So when you mirror the currents from the VCO, does it introduce extra dynamics in the loop?
Extra dynamic. Okay. So the question was, does doing this mirroring introduce extra dynamics into the loop? In steady state, not really. Having said that, starting these things up can be a little bit interesting. Okay. Now, anytime you do any self-bias kind of thing, the startup is always quote-unquote interesting. Okay. Now, it turns out with these loops, usually, as long as you make sure that the regulator starts up, everything else will kind of start. Because essentially what will happen is that once the oscillator starts going, everything else fairly quickly moves to kind of the parameter values it needs to be at to actually get the whole loop to kind of converge in the right direction. Because you can kind of think about it, you're just sort of tweaking the parameters of this linear system. So as long as you're tweaking them in a way that doesn't cause it to just completely go bonkers, eventually you should always get to the spot you really want to be at. But proving that is let's say more of a mathematical exercise than I think is worth in this particular class. There's entire, let's say, math classes you could take just on trying to prove that particular stability statement. Does that answer your question? Or by the way, it turns out things actually get even slightly more complicated than this, and we'll talk about that some more, probably not today, but probably next time. Because it turns out you're going to use this control voltage in a bunch of other places too. For example, you're going to use it to set edge rates in things like phase interpolators and things like that. And then very quickly you can end up with deadlock situations where different pieces of the loop starts at different times, and something else is going crazy relative to the other, and just you don't actually get a clock through. But we'll talk some more about that when we really get to those more complicated or more complete systems. Any other questions on this? Or? Okay, great. So if there's no other questions, then let's actually go ahead and move on to the next set of slides. So now that we've talked a lot about some of the components and sort of how you end up building these things up, the next thing I want to sort of spend a little bit of time on is just really from a performance standpoint, other than of course just how much power the PLL takes. The main thing you're really going to care about is just how much timing noise is it going to introduce into your overall link, right? And by timing noise, of course, I basically mean jitter. Now, before we sort of dive into too much detail there, let's just sort of remind ourselves, what is it that's going to be causing jitter? Like, why is it that fundamentally you're always going to have jitter in any system that you're dealing with?
You always have thermal noise.
Yeah, there's always some thermal noise. Now, how is it that thermal noise causes jitter? Like, what's the sort of physical mechanism that causes that?
Disturbs the edge crossings.
It disturbs the edge what? Ah, there we go. It disturbs the edge crossings, right? So imagine that I just have like something like an inverter, right? And I put an edge into that inverter. So ideally speaking, I get some edge coming out of the inverter, right? Well, but remember, when that inverter is actually transitioning, it's going to look something like, let's say I'm just pulling the output down, right, with capacitor initially charged, let's say to VDD. I'm just going to be pulling some current through there, right? Well, anytime I've got current flowing through that transistor, I've also got noise current flowing out of it, right? So in other words, if I took what used to be something that, as an example, would just be this, let's assume the transistor was a perfect current source, which of course isn't true, but let's pretend that it was. If ideally speaking, my edge at the output should look something like this, so let's call that V out versus time. If ideally it looks something like that, if I now add a little bit of noise currents into that output, well, guess what? I'm going to have these kind of wiggles on this waveform here, right? And so then if I kind of zoom in right on that VDD over 2 crossing, right? If I zoom in right there, what's basically going to happen is instead of me having a perfect sort of transition there, because of these, weird thingies, then basically the time, and let me draw this a little bit better, right? The time at which I actually made that edge crossing is different than what I nominally would have expected it to be, okay? So basically just that thermal noise, because it's causing a disturbance in the voltage, and because I don't instantaneously transition from one voltage to the other, that basically means that that uncertainty in voltage is translating into uncertainty in time, okay? So by the way, for that very same reason, it's not really just thermal noise, it's actually flicker noise will cause the same issue, right? Because basically if that flicker noise causes any uncertainty in the voltage, then again, that will translate into uncertainty in the time, okay? By the way, what else causes jitter? So there's definitely these fundamental, noise sources, but what else causes jitter?
Supply noise.
Yeah, exactly, supply noise, right? Now, the mechanism at which supply noise causes jitter tends to actually be a little bit different, okay? So for supply noise, it's not usually the sort of voltage uncertainty itself that causes it. It's actually more that you're modulating the characteristics of the circuits. Okay, so just as an example, if I take like an inverter again, and I modulated its supply voltage, then remember we said the delay is proportional to C VDD over I on, right? Then basically what's really happening is that when you change that supply voltage, you're modulating VDD over I on, okay? And that's what's actually causing the jitter there, okay? So keep these in mind because, again, the mechanisms are a little bit different. So when you go and sort of, let's say, do the calculations with these things, or really when you try and keep track of them in your overall budget, you have to keep track of which are the things that are really sort of fundamental noise sources that are unbounded, that are coming from just this voltage uncertainty. And what are things that are coming from just, hey, if you change the power supply voltage, you change the delay through your gate, and that causes some jitter at your output. Okay? Okay, so hopefully that's fairly clear. But let's actually now sort of take a closer look at what this means in terms of how noise in the different components, either supply or thermal, will basically go through the PLL loop and how it'll show up when it gets really to the output. Okay? So of course, the trick to remember here is that everything you can think of will add noise, right? So any component you add into the loop will add some noise into it. Okay? So because of that, you have to sort of keep track of what are each and every single one of these components going to do to you from the standpoint of how much jitter they create at the output. Okay? So what I want to do is basically look at what are the transfer functions from essentially the noise added from each component to the final jitter at the output. And the reason I'm going to walk through that is because you're going to see sort of things, different components in the loop contribute to jitter at the output in kind of different ways. Or rather, they get filtered in different ways. Okay? So let's just start out with the simplest one. So if I told you that I have a certain amount of jitter on this reference clock, what's the transfer function from jitter on that reference clock to jitter at your final output? And by the way, when I say jitter on the reference clock, I'm usually comparing it to some ideal reference, okay? To some ideal perfect clock that was always exactly at a particular frequency, okay? So what is that transfer function from jitter on the reference clock to jitter at the output? And again, I'm always comparing against some ideal reference. What is that transfer function?
Same thing that you wrote before.
Yeah, it's the same thing that we just spent, whatever, an hour and a half talking, or an hour talking about, right? That's just the transfer function, the reference transfer function of the PLL. Okay, so just, of course, as a reminder for everybody, I'll just write it in a slightly different way here. So here we're just saying that, phi out over phi ref is really just the H of the loop filter times KVCO over S divided by 1 plus H of the loop filter times KVCO over S over the divide ratio. Okay? And by the way, I included the 2 pi's here this time just to make it really clear. So what I've done here is this 1 over 2 pi, that's kind of like the normalized gain of the phase frequency detector. So in other words, it's taking phases and converting them to sort of relative to a reference period. Then I'm going through just whatever the loop filter transfer function is. So that's usually charge pump current times the impedance of the loop filter. Then I'm going through the KVCO. And in this case, and actually in most cases, most people specify that KVCO in units of hertz per volt. Okay? Not in radians per second per volt. Okay? So that's why if I do this way, I have to multiply by 2 pi afterwards to get to the radians at the end of the day. Okay? Now, notice that nicely enough, in terms of that forward transfer function there, this 1 over 2 pi just immediately cancels that 2 pi. Which is why, if you remember before, I was doing all those things and just dropping 2 pi's everywhere. That's how I was able to do that. I just mentioned them here because if you start injecting noises in other places in the loop, you can magically get those factors of 2 pi sneaking back up on you. Okay, so if you're not sort of careful about it, you can end up losing those factors of 2 pi, which unfortunately is a pretty big error to be making. Okay? So especially when you're dealing with jitter, just go ahead, write the 1 over 2 pi and the 2 pi, and then if you do things consistently, you'll be fine. Okay? All right, so this is indeed the reference, the transfer function. And again, just sort of as a reminder, if I look at the magnitude of that versus frequency, you're just going to get something that sort of looks like this. Right, so there's always at least a little bit of peaking because of the fact that there's the 0 in the forward transfer function. But basically you end up with something that looks sort of like a low pass, or really looks exactly like a low pass filter. Okay? Does this make sense to everybody? Or? Okay, so that's the reference. Now, before we sort of keep going from that, I just wanted to briefly mention, I think most of you have probably seen this at some point before, but it's actually interesting to look at what is the typical sort of phase noise spectrum or jitter spectrum you'd get from some reference source that somebody would give you, okay? So just to maybe sort of make things clear, what is the reference that you usually get? Like, what is that?
Oscillator of some sort.
Right, it's an oscillator. It may be built off of a crystal or some, LC tank or some laser or whatever, but it's just some oscillator, right? Now, because this is a reference, is there anything forcing the frequency of that oscillator to be some particular value? Or is it just, it is whatever it is? It just is whatever it is, right? It's some open loop oscillator. And it's just going at whatever frequency it is. Now, hopefully you've built that oscillator in a way that you've, slaved it to some physical quantities that have units of frequency, so you know very precisely what it is. But nonetheless, your reference is always just a free-running oscillator, okay? So if I sort of look at the phase noise or the jitter of that oscillator relative to some ideal perfect frequency, then what you almost always end up seeing is something that looks like this. And so what I'm basically drawing here is the magnitude of, or rather the power spectral density of the jitter. This is also actually the sort of the power spectral density of, let's say, the phase noise, if you prefer to think of it in the RF terms. If I do that versus frequency, and when I say frequency here, I mean sort of, again, I'm looking at jitter as being a waveform. And if I measured that jitter over time and I looked at the spectrum of that waveform, this is really what I'm plotting here. Okay? So what this typically looks like is something like this. Okay? There's always some region where that phase noise increases as 1 over f cubed. And then there's also a region where that thing increases, or rather basically has a slope of 1 over f squared. Okay? Now, by the way, the first question that almost always comes up here is, if I tell you that something goes with either 1 over f, or 1 over f squared, or 1 over f cubed, is, does it really go to infinity at DC? So now you guys tell me. Does the PSD go to infinity at DC or not? And to be clear, I'm asking about the PSD of the jitter.
Oh,
Yeah.
DC, it's not jitter anymore, right?
So what do you mean by that?
Well, I mean, it's your signal, really. It's your reference frequency.
Okay. You're sort of right, but remember, I'm always going to be comparing against some ideal perfect reference. Okay? So again, the question is at DC, meaning if I waited forever, will my jitter, meaning the exact arrival time of my edge, be, will it have infinite uncertainty in it?
Yeah.
Yeah, it will, right? Because remember, this is an oscillator, and it's free running, right? So let's just take a simple example. Let's say, even though these references are never built this way, because, CMOS ring oscillators are pretty crappy, but, the idea is actually the same, right? So let's say that magically I started out with one perfect edge, right? Okay, so I take my one perfect edge, I pass it through that first stage of the oscillator, right? Well, right here, because that first stage has some thermal noise on it, now already I'm going to have a little bit of jitter, right? Well, if I've got a little bit of jitter, and now I feed that into that second stage, well, guess what? That second stage is just going to take whatever jitter you gave me and add a little bit more jitter on top of it, right? Because it can't fix the jitter that you gave it in the first place, right? So now, okay, it's going to have even a little bit more jitter, right? Now you're going to take that edge that has even more jitter on it, of course, feed it to the next stage, and hey, guess what? Add some more jitter on top of that, right? And now, by the way, you're feeding that right back to the input, right? So I'm just going to keep on looping over and over like this and adding jitter as we go, right? Every single stage, I'm just going to be adding a little bit more jitter as I go, okay? So the whole sort of point of discussing this in this level of gory detail is that, indeed, if you looked at the phase error, if you wait forever, by definition, an open loop oscillator will have infinite phase error if you waited forever, okay? Now, in practice, this doesn't really matter because you almost always have something on the other side that's going to be figuring out what the nominal phase is supposed to be. And so it's just going to be sort of moving along with that oscillator as well. But in terms of, let's say, doing the calculations, it is important to keep in mind that you will indeed get infinite phase error at DC. Okay? Okay, so if I was trying to give you like a good reference, what would be the characteristics of a good reference? How would that change sort of this curve that I'm drawing here? What should a good reference look like?
It would be pushed down.
Yeah, first of all, you want it to be pushed down, right? So the farther down you can make it, the better. Okay? What else do you actually care a lot about? Particularly given that all your PLL is going to do to it is low-pass filter. What else do you care a lot about?
Want that corner to be at low frequency?
Yeah, you want that corner to be as low of a frequency as you can, right? So you want to take that corner and push it as far to the left as you can. Okay, so again, the trick or the point that I'm kind of trying to get at here is that typically speaking, in the PLL, unless you make the bandwidth really, really low, it's pretty hard to really do something about this 1 over f cubed region. Okay, so most of the time, all the PLL can really do is just try and give you some additional filtering on this 1 over f squared region here. Okay? So keep that in mind because, a little bit later on, we'll be talking about sort of some of the trade-offs in the design of the overall loop. They're really pretty tightly tied to what is it that you can really filter in terms of the reference noise, and what is it you can actually filter in terms of all of the rest of the noise in the loop. Okay? Does this make sense to everybody? Or? Okay, so let's move on to, there was a couple questions. Yeah?
I guess, why do you care about the 1 over f cubed noise? Isn't it just kind of slow varying phase error?
So it depends what you're doing, right? So if this is at a low enough frequency that, for example, your CDR on the other side just tracks it out, then maybe you don't actually care, right? But if it's not at that low of a frequency, or, for example, your CDR has a very, very low loop bandwidth, which we'll talk about reasons why you might have to do that a little bit later on, then you'd actually start seeing some of that jitter. Okay, so you're absolutely right. It really depends on what's the system on the other side that's dealing with sort of this clock jitter.
So can you explain once again why you want that 1 over f cube corner to be as inside as possible?
Because basically if you sort of think about it, if I just make a comparison between two things, let's say I have one that looks like this, and I have another one where I've pushed that 1 over f cubed corner in, right, something like this, then just the net jitter that I have is smaller to begin with. That's all.
I thought you're just taking that and you're pushing it. So, then it would have gone up. But
well, right, but if I push the... Oh, I see. Well, okay.
It's clear now. Yeah.
Right.
Yeah, got it.
Okay, other questions? Or okay, so that's what happens with reference. Now, let's look at the next sort of, let's say, obvious component in the loop, which is the phase frequency detector. Okay? So, first of all, let's just, make sure that we're clear. Why is it that a phase frequency detector should add jitter into the loop? What is it about the PFD that's adding jitter? What does a PFD look like? How do you build it? Say that again?
Charge pod?
I'm talking still about the phase frequency detector, not the charge pump, not the loop filter yet.
There are no flip
Two
flops.
latches in there.
Yeah, it's just two flops, right? So, as an example, it typically looks something like that. Right, and then of course I have the AND gate here, and that goes to reset both of the flops. Okay? All right, and then I've got my up, and I've got my down. Right, let's say ref and feedback. Okay? So why does that add jitter?
Feedback clock has jitter. That's right.
Feedback clock had jitter. The feedback clock does have jitter, but I wouldn't necessarily say that that's, the fact that it had jitter was true to begin with. That's not necessarily caused by the PFD, right? So what about the PFD is causing this thing to have jitter?
Driven off of the nominal digital supply, so that.
Okay. So indeed, there may indeed be some jitter just due to the fact that it's running off of a digital supply, and that supply, or just any supply, and that supply could be varying. That is true.
Noise from the transistors.
Yeah, there we go. Noise from the transistors, right? So basically, remember, what I'm going to be creating at the output over here is these two pulses, right? Something that look like this. Well, hey, the width of that pulse is set by some delays of gates inside of here, right? Hey, those delays have jitter on them, okay? So in fact, if you really sort of look at this, let's say more carefully, what's going to happen is you're going to have some jitter on that edge. In fact, you're actually going to get some jitter on this falling edge as well. In fact, you're going to get it on the down pulse also, and of course also on this other edge of the down pulse. Okay? So basically, just because of the fact that this is just some gate with some delay in it, that means that you're actually going to get some jitter due to that phase frequency detector. Okay? Okay, so because we're sort of on this topic of, digital gates actually adding jitter, what I quickly want to do is just talk a little bit about how much jitter do you really get from having some digital gates. Okay? Because this is kind of actually a good way of reviewing or making sure we understand where is it the jitter is really coming from in the first place. Okay? So the very sort of simple situation that I want to figure out is, let's just say that I have some inverter, okay, and it's driving some load capacitance, okay? And in this particular case, what I'm going to do is I'm going to put just a rising step into it. And of course, it's running off of some power supply, okay? So for now, let's just assume the power supply is perfect. We'll come back and see what happens really when I put variations on the supply later. So let's assume that supply is perfect. Okay, and let's assume that I'm even really nice and I give you a perfect step at the input. Okay? So what I want to do now is try and draw a model that will let me figure out how much jitter should I get at the edge at the output. Okay? So what do I need to do that? What are sort of the important things to keep in mind? What would be like the simple model that I would draw to just figure out what the delay of this thing was in the first place? Yeah, I would basically say that I've got a current source, right, which is just sort of the ion of my transistor, right? And I've got that driving a capacitor. Now, what's important about the capacitor in this context? Like, what do I have to specify for me to figure out the delay? Well, okay, yes, obviously I have to tell you the value. That's true. Anything else?
Initial value.
The initial condition, right? Okay, and by the way, you'll see why I've pointed this out in such gore detail in 1 second, right? Because what we're basically saying is that if I want to know a delay, then I need to know where did that capacitor start from, how much current did I pull off of it, and then how long did it take from the time the input arrived to the time at which I cross VDD over 2. Okay? Now, from the standpoint of noise, it turns out there's two things that I need to sort of keep track of in this model, or maybe add into this model, to figure out how I'm going to be getting jitter. So what's the first and hopefully most obvious thing that I needed to add this model to actually figure out why I have jitter, or how much jitter I'm going to be getting?
Source.
Yeah, so first of all, I have a noise current over here. Right? Just if I have a transistor that's on in saturation or whatever it is, it also has a noise current associated with it. Okay? So let's just call that IN. There's one more thing which is slightly subtle, which I still have to add to this to actually figure out how much total jitter I have. So what's the other thing I have to add?
Noise. The noise sampled on C.
Ah, there we go. It's actually the noise that I initially sampled onto that output capacitor. Right? Because remember, this initial voltage here, guess what? It's got some thermal noise on it, right? So right when you put that step input, you're going to be sampling some noise, some voltage noise onto that output capacitor, right? And if you start at a different point, the time at which you cross VDD over 2 will be different, okay? So indeed, this V initial here has to include sampled noise. Okay, now, by the way, how much noise will you sample onto that capacitor? Right when you put that input to step from ground to VDD, how much noise do you sample onto the capacitor?
KT on C.
Yeah, KT over C, right? Okay, so now if I want to figure out how much jitter that initial sample of noise causes, what is that going to be? What's that going to be set by? And by the way, this is, of course, the sigma voltage noise squared. Okay, so if I just told you whatever that initial voltage error was, how would you translate that voltage error into a timing error?
The fall time, or the slope.
Yeah, exactly. What you need to know is what's the slope of the waveform, right? So you'd basically say that your sigma of the jitter, due to that initial sampled voltage error, would basically be that voltage error times the fall time divided by what? And by fall time, I just mean, you know, this thing here would be like T fall.
Or V initial.
By the way, okay, you're actually right. So let me just be very clear. Let me say that this V initial here is just equal to VDD plus V error. Okay? So that V error is basically just that KT over C noise that I've sampled. Okay? So what's sort of the slope of this waveform here? If I told you the fall time is T fall, and that nominally speaking at least you started at about VDD, what's the slope?
Lower T fall.
Yeah, exactly. So basically what we're saying is that my timing jitter should just be equal to my initial voltage error times my T fall divided by VDD. Okay, and again, nicely enough, the dimensions of this work out because we're just sort of saying if I take my normalized voltage error and multiply it by whatever my fall time was in the first place, that's how much jitter I should expect to get. Okay? Does this make sense to people, or? Okay, now, turns out that actually, just by sort of putting these things together, we can actually figure things out in a slightly more, let's say, intuitive or useful form. And so, at the end of the day, it's really just saying what I've said here, but I'm just going to sort of write things out in a slightly different way to kind of highlight, let's say, the more fundamental trade-off that we're dealing with. Okay? So we already said that this KT over C is kind of the noise that we're going to be sampling, right? What is T fall? What is that set by?
VDD over I.
Yeah, exactly. That's just set by C, VDD, divided by the on current, right? Okay, well, so what I'm going to do now is something that looks slightly counterintuitive, but you know, it's just going to be a mechanism for us to get it into a particular form. Just given that fact, I can kind of say that the capacitance, and by the way, this is a proportionality constant here. There's actually a factor of 2 that you need to be careful about, but you know, I'm not going to worry about that too much right now. The capacitance I'm going to say then is actually E proportional to the fall time times the on current divided by VDD. Okay? Again, I'm just rearranging things because if I then do that, then I can say that the sigma squared of the jitter is just going to be equal to, of course, the voltage error squared, which remember was just KT over C, right? But now I'm going to just replace that C with this expression that I just wrote, which is T fall times I on, and then VDD on the top over here. Okay? Then it's just going to be times, because I'm in the sigma squared rather than the sigma, it's just times T fall squared over VDD squared. Okay? Did everybody track that? Or so in other words, this whole thing right here is just 1 over C. Okay? Does this make sense to people? Or okay, now why did I do this? Because notice, if I just simplify this slightly, then I can say that the sigma squared of the jitter is just at least proportional to KT. Notice this VDD squared cancels that VDD. This T fall cancels one of those. And actually, did I do that right? No, wait, hang on. Squared. Yeah, no, okay, that's right. So then what you end up with is KT over VDD times I on times T fall. Okay? So why do you guys think that I sort of put it into this form? What's kind of appealing about this particular form here? What does it tell you?
Larger delay leads to larger jitter.
Exactly. First of all, it tells you if you've got a bigger fall time, which means you have bigger delay, you've got more jitter. Okay? Now, by the way, what's the units of VDD times I on?
Power.
It's power, right? So what do you have to do to get lower jitter?
1
burn more power, right? Now, by the way, that shouldn't be particularly surprising because in general, if you want lower noise, you need to burn more power. But guess what? Same thing is true in the jitter domain as well, in the timing domain. So in other words, this is basically telling you if you want to know how much jitter you're going to get simply from the fact that you sampled an error voltage to begin with, then already you can see that you actually need to just burn more power in order to be able to reduce that amount of jitter. Okay? Either you put more capacitance or you have more voltage or whatever it is you have to do. Basically, you have to burn more power. Okay? Does that make sense to people? Or? Okay, so we've gotten actually one of the components of jitter, which is due to this initial condition. There's still going to be jitter due to this current noise that we're going to integrate. But since we're out of time for today, I think we'll finish up with that next time. So I'll see you guys on Thursday.